Stellar remnants. Eventually, all stars consume their nuclear fuel and collapse into one of three final states: white dwarf, neutron star, or black hole. White dwarfs are extremely small stars with densities greater than any known terrestrial material. It is believed that white dwarfs began life as low-mass or medium-mass stars. As the star ages, it begins to collapse, becoming a dwarf, because it no longer produces sufficient radiant heat to counteract the contracting force of its gravity. Although some white dwarfs are no larger than Earth, the mass of such a dwarf can equal 1.4 times that of the Sun. A spoonful of such matter would weigh several tons. As a star contracts into a white dwarf, its surface becomes very hot and very bright. But without a continuing source of energy, it will slowly become cooler and dimmer. Although none have been observed, the terminal stage of a white dwarf must be a small, cold, non-luminous body called a black dwarf. A study of white dwarfs produced what might at first appear to be a surprising conclusion. The smallest white dwarfs are the most massive, and the largest white dwarfs are the least massive. The explanation for this is that a more massive star has a greater gravitational force, and that greater gravitational force contracts the star into a smaller, more densely packed object than one gets with a less massive star. Thus, the smallest white dwarfs came from the collapse of stars that were larger and more massive than those the large white dwarfs came from. Extending this idea of larger stars collapsing to smaller stars leads to the prediction that very large stars would collapse to stars even smaller and more massive than white dwarfs. Named neutron stars, these objects are thought to be the remnants of supernova events, the collapse of a large, very massive star. If Earth were to collapse to the density of a neutron star, it would have a diameter equivalent to the length of a football field, and a pea-sized sample of this matter would weigh 100 million tons. This is approximately the density of an atomic nucleus. Thus, neutron stars can be thought of as large atomic nuclei. Although neutron stars have high surface temperatures, their small size would greatly limit their luminosity. Consequently, locating one visually would be extremely difficult. However, theory predicts that a neutron star would have a very strong magnetic field. Further, as a star collapses, it will rotate faster, for the same reason ice skaters rotate faster as they pull in their arms. If the sun were to collapse to the size of a neutron star, it would increase its rate of rotation from once every 25 days to nearly 1,000 times per second. The radio waves generated by such rotating stars would be concentrated into two narrow beams, like the rotating light on a police car or ambulance. If Earth happened to be in the path of this beacon, the star would appear to blink on and off or pulsate as the radio waves swept past. In the early 1970s, a source that radiates short pulses of radio energy, called a pulsar, pulsating radio source, was discovered in the Crab Nebula. Visual inspection of this radio source revealed it to be a small star centered in the nebula. The first neutron star had been discovered. Are neutron stars made of the densest matter possible? No. During a supernova event, remnants of stars greater than 3 solar masses apparently collapse into objects even smaller and denser than neutron stars. Even though these objects would be very hot, their gravity would be so immense that even light could not escape the surface. Consequently, they would literally disappear from sight. These incredible bodies have appropriately been named black holes. Anything that moved too near a black hole would be swept in by its irresistible gravity and annihilated. How can astronomers find an object whose gravitational field prevents the escape of all matter and energy? Theory predicts that as matter is pulled into a black hole, it should become very hot and emit a flood of X-rays before being engulfed. The first black hole X-ray sources were discovered in 1971 by detectors on satellites.